Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing a crash course on the topic of deformation of solids for Cambridge AS Physics, subject code 9702. Now, the topic of deformation of solids, although a short one, can be very complicated. So basically in this topic, what we want to do is understand how when a solid changes its size or shape, it can actually store energy. And we want to know how it does this, but we also want to know how it will actually change its shape and whether it will actually ever return to its original shape. So some of these facts are very important because we apply them across other branches of physics and even into the second year of A-level physics. So where do we start on a topic like this? Well, we start with something that seems simple, but again also can get very complicated, and that's Hooke's law. So before we get into what exactly Hooke's law is, let's look at a situation where I have a spring and a mass attached to a spring. So let's say I have a vertical ceiling or some vertical placeholder that I can use to hold my spring. And what I will have is that when there's nothing attached to the spring will hang such that doesn't really extend that much, and so its length that we measure is the original length, or sometimes called the natural length of the spring. Now this can apply to all solids, but you'll see that we prefer springs because springs are, well, springy. Things can compress, they can undergo compression, they can undergo tension, we can extend them, we can compress them, and we can use them to store energy. If I hang a mass at the end of the spring and it has a weight W, we'll see that each loop in the spring will be further apart and the spring extends. And I'll just hang a block, maybe a wooden block with weight W, and the force that is applied to the spring in order to extend the spring, the tension, the tensile force, we call it the load. So the load is the force that is actually causing the spring to extend, and the difference, or the additional length that the spring now takes on, is called the extension. And you'll see later on we give this the symbol E, small letter E. And so the original length and extension are not the same length. Obviously the extension is the increase over the original length that the spring now has. And because the spring is undergoing tension, we can call this tensile deformation. Again, to deform means to change the size or the shape of something. In this case, we are changing the size of the spring by extending it. If I were to compress the spring, another thing springs can do, then I have compressive deformation. So compression and tension meaning the pulling of the spring, and compression meaning the pushing of the spring, making the spring smaller. And might seem obvious, but the extension is, and what we'll do actually is we'll label this entire length from the ceiling to the bottom of the spring as the extended length. Now that the spring has been extended, the total length is called the extended length. Just so we can write a mathematical formula that's saying that the extension is the new length, which is the extended length, minus the original length, or minus the natural length, whatever you would like to call it. And this is how we can find the extension in a spring. Now it's important that I introduce this because extension is a concept that we need to understand. I'm not saying that the length of the spring is the extension. I'm saying the increase in length of the spring is the extension. So what we find is that for most springs, if not all springs, there's a very nice relationship up until a point between the load that you place on the spring. So let's imagine for simplicity's sake that we're talking about a spring and a mass hanging at the bottom of the spring, as I drew above. So if I were to sketch a graph of load against extension, and you could try this if you had a spring on you and a mass that you could tape to the end or stick to the end, that the load against extension graph is actually a straight line up until a point. So I'm going to label the point at the origin A, so you see when there's no load, then there's no extension of the spring. The spring is at its natural length. And this is a straight line curve until it reaches a point B. And then something weird happens. It begins to curve. And so you can get more extension for the same load once you pass this point B. And it's no longer a straight graph, it's now curved. And what we say is that B is the limit of proportionality. What does this mean? That means that the extension is proportional to the load, but there comes a point where there's no longer that proportionality. And I can extend the spring even more with not that much of an increase in the load. So the limit of proportionality is the point by which when I start taking readings of extension, I find that the load is not increasing in those same increments as they were. And so B is called the limit of proportionality. Now, Hooke's law deals with the straight portion of the graph from A to B. So as you may have seen before, and we can write this down in words, but we can also write this down mathematically. But Hooke's law basically says that if we're going from A to B, if I look at the straight portion of the graph, then obviously we can see the load is proportional to the extension. So anywhere between A and B. I don't always have to say extension. If I'm compressing the spring, then instead of extension, I can say reduced length. We're just talking about extension now just for simplicity, but if I'm compressing, then I can say reduced length. Or whatever other word will fit for compressing the spring. And so what this means is force is equal to some constant multiplied by the extension, and we'll give the extension the symbol lowercase e. So it turns out that this lowercase, or this value k, is the force applied per unit extension, and we call this, well, in this case, if the solid is a spring, we call this the spring constant. We also sometimes call this the force constant. So spring constant, force constant, or force per unit extension. I think the most general term is probably force constant. So it is the force per unit extension. And we can see from here that the units of measurement, I'll use the square brackets for units of measurement for K, is a Newton per meter. How many newtons do I require to extend the spring by a meter? Sometimes we measure them in Newton per centimeter, etc. But it's basically a force multiplied by a force divided rather by a distance. And so this is Hooke's law. Well, in words, you'll see it better if you're reading a textbook, but in mathematical form, F is equal to KE. Sometimes F is equal to KX or K delta X. Delta X is fine. E is fine. X could be a bit ambiguous because X makes you think you're measuring the length of the spring when you actually need to measure the extension of the spring. And so Young's law, Hooke's law rather, is not too difficult to understand. But remember, it only applies for the portion from A to B where the graph is straight, where there is a proportionality between force and extension. And this is what I actually wanted to introduce, which is the Young modulus. Now, the Young modulus tells us how these forces can be investigated. So let's first try a scenario. Let me draw, again, I don't always have to deal with the spring. I could deal with any solid. So I'm going to assume that I now have a solid that's a cylinder. So a solid uniform cylinder that has the same mass throughout, the same mass per unit length throughout. And I'm going to apply a tensile force on the cylinder, and I'm going to stretch it out. So it's not necessarily a very stretchy material, but even still I can apply a force and make it stretch outwards. Its original length, we'll call it L0, its natural length. But I then apply some, and obviously this is an exaggerated diagram, but I then apply some tensile force, and what I find is that the length of the cylinder increases. And the increase in length of the cylinder we'll call the extension E, just like we did for the spring. And this only happens when there's some load or some force that is being exerted on the end of the cylinder, in this case to the left. And basically what happens is the length has now changed because of the extension. And so we have a before scenario and we have an after scenario. So the initial length was L0, and then the length changed to L0 plus E effectively when the load was added to the cylinder. So before we talk about the Young modulus, we need to define something called strain. And if you study material science, obviously these words will be a lot more familiar to you in the future. But the strain is defined as the extension of a solid divided by the original length of that solid. So I apply a force or a load like I have above. The solid extends. If I take the extension E divided by the original length, I get the strain, basically by how much the length has changed. And we give it the symbol epsilon, the Greek letter epsilon, and we can write this as little e divided by L0. And what we can see from here is that it's a length divided by a length, so it doesn't have any units. So epsilon itself is dimensionless. This is what we call the strain. Another quantity that we want to define is called the stress. Not the type of stress that you're going through currently with exams, but similar nonetheless. The stress is actually, I need to just, before I get ahead of myself, let's draw another diagram, shall we? And let's change the picture up just slightly. And instead of a cylinder, let's draw the slice of a cube. So a very thin slice of some cubic solid. Again, it's some exaggerated diagram, not drawn very well at all, but I think you get the idea. So it's the slice of some cube, and this solid, yeah, well, I could pretty much guarantee that I could do a better job than that. Okay, so this is a slice of some solid. It has an upper surface area of A, and then there's some, maybe we put some heavy mass on top of it, and the weight of that mass is F. The load that we apply onto the solid is F. So the stress is defined as this force F, whatever the magnitude of that force is, divided by the area that is normal to the force. So in this case, that area is the area A, because the entire area A is perpendicular to the force. The force comes in down at right angles to the area at any point. And so we give this the letter sigma, the Greek letter sigma. And sigma is equal to the force per unit area, F over A. And the units of measurement will be similar to that of pressure, Newton per square meter, or we usually use pascals. So the stress is the force that is applied on the object divided by its area. If I have a high force, I have a high stress. Also, if I have a smaller area, I have a higher stress. And so kind of like equivalent to pressure. Actually, it is equivalent to pressure, but for a solid. And what we find is that stress is related to the load, to the force, and strain is related to the extension. And so there's a similarity in the graphs, and the graphs of load against extension and the graph of stress versus strain, because of their relationships with load and extension. So if I draw a graph of stress on the y-axis and strain on the x-axis, what I get is another straight line graph. So as stress increases, strain increases, vice versa. I then reach a point, I'll call it P, and the graph begins to curve a bit. And that point P is, before point P, the graph is a straight line. So P, just like before, is called the limit of proportionality. It is the limit before which everything is proportional and after which there is no proportionality. And so that's a sketch of the graph of stress versus strain. So what does this mean? That means that stress is proportional to strain, well, at least until the point P. But that means that, remember, if I want to turn a proportionality into an equation, I need a constant. So I can say stress is equal to some constant E multiplied by strain. Now it turns out that this constant is called the Young modulus, named after someone called Young. So it is just a constant that relates stress to strain. So Young's modulus, or the Young modulus, is E. It is this constant. And so from this equation, this constant E is stress over strain, which is sigma over epsilon, using the symbols that we've given them, which is sigma is F over A, force per unit area, that's the stress, multiplied by 1 over epsilon, which is L naught, original length, over extension E. So we can write E, or uppercase E rather, Young modulus, as the force times the original length over A, the area, times the extension E. So uppercase E is F L naught over A times lowercase e. This is an expression that will always help you when you're trying to figure out, well, how the Young modulus will change if we increase the force, if we increase the area, if we decrease the extension, and so on. So that's a relationship between our Young modulus and stress and strain. And so, I mean, it looks okay on paper. There's nothing really complicated, but I'll just put an example up on the screen, and we'll go through the example just to see that we really understand how to manipulate this equation and understand it in different ways. So here's an example that I've taken from a past exam paper. And at some point we will do the maybe Papa Cambridge topical problems that may have questions, well, we'll have questions similar to this, maybe even this question itself. But this is just part of a question that deals with Young modulus and stress and strain and so on. We're told that a copper wire of uniform cross-sectional area 1.54 times 10 to the minus 6 square meters and length 1.75 meters has a breaking stress of 2.2 times 10 to the 8 pascals, and the Young modulus of copper is 1.2 times 10 to the power 11 pascals. We are asked to calculate the breaking force of the wire. Now, whenever you're asked to deal with wires, always assume that wires are cylinders. In general, wires are cylinders unless stated otherwise. Just very, very small cylinders with tiny diameters, and hence they have tiny cross-sectional areas. Now, if I want to find the breaking force of the wire, and I'm given the breaking stress, I need to know what force is going to cause the stress to reach this value so that the wire will break. So the equation for stress, which is sigma, is force per unit area, F over A, which means the force is equal to sigma times A. And if I put values in, the breaking stress is 2.2 times 10 to the power 8 pascals, that's SI units, so that's fine, times the area also given, without any conversions needed, 1.4 times 10 to the minus 6 square meters, and what we get is 3.388 times 10 to the power 2. and that's newtons. So in 3 significant figures, I can write this as 339 newtons, or 3.39 times 10 to the power 2 newtons. That's the braking force of the wire. So that requires us to know how we can relate force to stress, or load to stress. We're then told that a stress of 9 times 10 to the 7 pascals is applied to the wire, and we want to find the extension. So now we apply the load, and we want to know what the extension is going to be. Well, I was given the Young modulus for copper, and that will apply for any copper, despite the shape and the size, etc. And I'm given Young modulus, so I'm probably going to need it somewhere. So I know that the Young modulus is stress over strain, stress over the value epsilon. But I'm not given the strain, I'm just told find the extension. So what I can do is write the strain as its base equation, which is extension over original length. So the stress is given, so I can leave sigma as is, multiply by the original length L naught divided by the extension little e. And now I have an expression that I can actually use to solve for the extension little e. Little e is sigma L naught over big E. And all of these values are known. So the stress, I'm told, is 9 times 10 to the power 7 pascal, so well within the braking stress, times the length of this wire is 1.75 meters, which was given as well, and the Young modulus was 1.2 times 10 to the power 11 pascals. So we can just double check our length is correct and our Young modulus is correct. And so if we do this calculation, we get 1.3 times 10 to the minus 3 meters. We'll keep our answer in 2 significant figures. 1.3 times 10 to the minus 3 meters. And so that's how you can apply the expressions for Young modulus, for stress and strain in solving problems. Now, yes, the problems can have multiple variations, but this was just a quick summary of how we can understand Young modulus and stress and strain. And so that was things to do with the Young modulus, which may be familiar to some of you, but I think in general it's probably something quite new, if not completely new. Now, another thing that we need to talk about is elastic and plastic behavior. So what does elastic and plastic behavior actually mean? So we talked about the limit of proportionality, but we also need to talk about what elastic deformation means. So in a nutshell, if I can deform a solid and the solid returns to its original shape and size when the force is removed, it undergoes elastic deformation. So what this means is the object returns to its original shape and size when the load is removed, or when the force is removed. And we call this elastic deformation. Okay, so I have to retype that apparently. So the object returns like a spring. You stretch a spring, you don't stretch it too far. With a small force, it will go back to its original shape. So it returns to its original shape and size when the force is removed. Okay. So we have success finally. Elastic deformation is when the object returns to its original shape and size when the load or when the force is removed. The other type of deformation that we have is called plastic deformation, spelled just like the word plastic that you know. And obviously you can see what this means. This means if I apply a force, but I apply a force that's too great, what's going to happen is that the object is not going to return to its original size and shape when the force is removed. So it's going to be completely deformed or deformed permanently. So I'm simply going to change this to say the object does not return to its original shape and size when the force is removed. So that's the difference between elastic and plastic deformation. And this can happen if I stretch a spring too far, and once I pass that point where it cannot undergo elastic deformation, it'll undergo plastic deformation, and it'll permanently lose its original shape, and that's when I need to get a new spring. And so I can then sketch. I can go back to my graph of force and extension, or load and extension. And I can just point out some interesting points on this graph especially. So we know that this graph is a straight line up until a point, and we call that point A. And then the graph begins to curve, but there's another point B that we need to mention. And what we said before still holds. A is the limit of proportionality. We're just adding a new point on this graph now. So A is the limit of proportionality, meaning up until A, the force or the load is proportional to the extension. Increase the force, the greater the extension I'm going to get on the spring. But the point B is just past the limit of proportionality, and we call this the elastic limit. The elastic limit is the limit below which the deformation will be elastic and above which the deformation will be plastic. So what we can say is that this is the maximum extension that will allow for elastic deformation. So any extension greater than this, and we have plastic deformation. So you can see it's slightly above usually slightly above the limit of proportionality. So even though it's not proportional from A to B, you can still save the spring, but anything past B and the spring is completely deformed permanently, doesn't return to its original shape and size. If you do have a spring that you can spare, you can try this, and you can see that there's a point at which when you increase the force, well, a small spring in the lab that is, there will be a point at which you can apply too much of a force and you're not going to get the spring back to its original size and shape. So why is it important? Why do we talk about, well, springs particularly rather than just solids? Well, it's important for solids, but it's also important in things that we generally use to store energy. We don't generally use oddly shaped objects in the lab to store energy when we compress or put them under tensile stress, but what we do is store energy in springs. And because springs are easy to compress, easy to deform, they store what we call elastic potential energy. So they store energy when we compress them, and they store energy when we expand them. And that's because we are doing work on the object for them to undergo compression or tension. So what is elastic potential energy? Again, just being lazy, I'm going to type it in saying energy that is stored in an object due to a change in its shape or size due to its deformation, which is recovered when the force is removed, provided the object hasn't gone past its elastic limit. So there's energy stored in objects when objects or solids change their size or shape, and the energy is recovered when the force is removed. So I can do work on an object. I can do work on a spring by compressing it or by pulling it apart, and then I can use that energy for something else. We know that if I compress a spring with a mass, maybe I push a mass against a spring and I let go, the spring will push the mass out because the energy is stored as elastic potential energy, which is a type of potential energy. And so how do we find what this energy will be? Well, I'm going to just draw a graph on the side here. Again, your favorite graph for this topic, the force against extension graph. And this is going to help me uncover what the energy is going to be. Now, we have to be careful here. The force is not constant. The force here is increasing as the extension is increasing. So the both are actually changing. I don't have a constant force being applied. So when I want to talk about the work done on the spring, I'm going to have to talk about something very specific. So the work done in compressing the spring, or extending the spring in this case, is the potential energy that is going to be stored in the spring if I extend it or compress it. And this will be the average force. I have to take the average force because the force is changing as we go from 0 to some extension E. I'll call the force F and the extension E, the point in question. And it's the average force multiplied by the extension. And we have to use the average force because the force is not constant. When we say work done, we say force times distance in the direction of the force, but that's for constant forces. And if I were to shade this area, that average force would multiplied by the extension would be the area under graph. So the area that is shaded, the shaded area, the area under the graph from 0 to the extension. And so what this is, since this is a triangle, is a half Fe, which kind of makes sense. A half of the force, the average force will be half of the final force. And so that's a half Fe. And the work done is equal to the potential energy stored. And so I can store an energy of a half Fe in the spring, which then can be converted to kinetic and other forms of energy when the potential energy is released. And we can also write this in another way. We can also say that F is CAIE, which means that we can write the potential energy stored in the spring, the elastic potential energy, as a half KE squared, sometimes written as a half KX squared. And just like any other type of energy, the unit of measurement of elastic potential energy is joules. So we have two expressions for elastic potential energy. I can obviously choose which one I'm more comfortable with. They're both basically two forms of the same thing. But this is just a type of energy, like we have kinetic energy, a half mv squared, and gravitational potential energy near the Earth's surface is mgh. This is another type of energy. And again, this energy can be converted to other types of energy. And we need to understand that that's why this energy is important. If I fire a block from a compressed spring, it initially has an energy of a half KE squared, which eventually will become kinetic, a half mv squared. So we can use it in energy conservation questions and so on. And that's basically all for this topic. I hope this crash course was helpful. If it was, please leave a like, leave a comment, subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.